how we think about this well depth, and anything above this will become difficult to take out, once you get trapped into this well. So this is kind of a picture for general material that we see in nature, that you throw gas particles to system, and you expect they all have this kind of idea that there will be a Feezy absorption state, as in what happened, as in freezing. So when you freeze a material at cold temperature, here you're just initially just when the well into action. There's no direct, and when I say direct interaction, what do I mean by that? I mean that there's a real bond formation between your absorbent, your particle, and the surface atom itself. Okay, so that's really real sharing of electron, right? This is why it's so strong, because now this electron sharing, electron transfer between your absorbent and the surface, and they are stuck together, and that becomes very strong, very hard to pick up. And this Feezy absorption state, of course, a good example will be like xenon atoms on any surfaces. And xenon, of course, is a new gas noble element, and it had no interaction. The electronic shell is totally enclosed. Very hard to share electron with any kind of noble inert gas type particle, and you only would see Feezy absorption state like that. There's no electron sharing between your xenon atom and any absorbent, any substrate, any nickel surface or metal surface, if that is your surface. Okay. Where chemical absorption, a good example of chemical absorption will be classic CO on any metal surfaces, CO on copper, CO on nickel surfaces. The CO bond is very strong, and there's real electron transfer between the CO molecule and your metal atom. In the classic organometallic chemistry sense, you have a sigma donation between carbon and the metal, and then you have pi bond back donation from the metal atom into your CO molecule. That's why CO absorption is a classic chemical absorption system, and it's very, very strong. Okay, so those are the picture. Those are the sort of idea that we have now. How do we probe this type of interaction? How do we learn a little bit about this gas surface interaction? And the common technique that people think about is basically collision theory one more time. You're basically throwing particle atom scattering. You're creating an atomic beam, and you collide this beam with your surface, and then you see what happens to it. Okay, so that's basically what the common approach of looking for this. And so the idea is very simple. The idea is that as your initial particle beam comes in like this, it's going to have a certain kinetic energy, and as you approach a potential well, okay, so this is the potential well near your surface, right? Your particle is going to experience an acceleration, an increase in kinetic energy, because you have approaching a potential well like this. So the kinetic energy is going to go up and then come back down. So if you can track the kinetic energy of the movement, of your particle beam, you could probe what is the potential of this interaction, this well, this type of structure that you see. And people had done a fair amount of work on this type of using this type of atom scattering type techniques. And there are a couple of considerations. So just a little bit of jargons here, that you have something called so when you scatter stuff, a particle beam onto your surface. Of course, we don't think of a totally flat surface like this, right? If you have a Mueller type, extreme atomically flat surface, what happens is that you hit your particle in a normal direction, right? Normal coming in a normal to your surface, the atom just bounces back. The reflection angle just bounces back. Okay? But of course, the surface itself is not totally atomically flat. It is, however, has so-called congrugations, meaning that you have this roughness on the surface. And depending on the size of your roughness, how surface roughness is often defined how high the average of these bumps are over a certain area. So depending on how big these bumps are, right, this roughness that you have different type of scattering phenomena. So here, for example, if you have a roughness like this, you consider all this incident being normal to it. Okay, these are my incoming beam. You can see, depending on where it goes, where it hit this curved surface that I have, my reflected beam could be at different angles. Okay, and this is often known as rainbow scattering because this different angle, right? This outgoing angle like this, the particle beam coming out like this. This whole range of angle effectively is kind of like a little. It's kind of like your light hitting a droplet of water, right? It's hitting a droplet of water, and your wavelength of this light is much smaller than the width, the scattering width, right? The width that the light go in this water droplet, and you see, right, in a rainy day like this, you look outside and you see a rainbow color. And the reason is because of that. When you come in at different angle, you have a scattering effect. This scattering effect which disperse in all direction and change the wavelength. In most cases, give you different color because of that. Okay. So this is classical, so-called classical rainbow scattering. And if you look at these different roughness that you can see that at a certain angle, depending on how deep this congregation is, right, you could have this return angle, direct return angle, limited direct return angle coming back, and you can know how wide from this return angle that you see. Because in other words, what I'm saying is that it limits the range of your rainbow scattering. You can only scatter in a certain range, and then you will get cut off. You cannot measure anymore once you're above that angle. Just like here. Okay, so here's a plot of your backscatter atom beam direction. So you have this rainbow angle, so-called rainbow angles, which is the limit of which you can see any particle beam, the angle from which you can see. Outside this angle, you do not see any particle beam at all. So you start from zero angle, which is normal emission, and then as you go higher and higher, you will get chopped off. And this chop off, this range here, depends on the roughness of the surface that you have. Okay? So immediately, using classical scattering, you already can sort of get a sense of the roughness of the surface that you have by looking at this refracted angle, the maximum so-called rainbow scattering angle that you see here. Okay, so let me talk a little bit more about this in a kinetic sense. What is the picture that we got when we forward particle beam to the surface? So here we have a particle beam, high particle coming in, highlighted in red, hit the surface. It may bounce away right away, but most of the time it probably hang around. It probably interact with the surface in some time scale. It could be very short time scale or very long time scale. There may be interaction between this particle, right? This absorbing now, once this is absorbed, with the surface atom itself.